Morning, everybody. Morning. So before I start chapter 27, just a little bit, something I didn't get to last time that had to do with energy vampires.
Yes.
And I'm talking about the actual energy, not the psychological ones. So an energy vampire is any device that draws electrical energy when it's turned off. Can you think of any things in your homes that do this?
Always something that stores energy.
Not stores.
Wi-Fi.
Wi-Fi? No. Okay, so Wi-Fi technically is not an energy vampire, right? Because the router is on doing its job. I'm talking about things you turn off.
TV.
Television, okay, that still draw electrical energy when they're off.
Does it support that red light message?
So, one of the things you need to do, okay, is that you need to, tonight, in your home, room, wherever it is that you abide, turn off all the lights and then look at all the lights that are blinking back at you. Okay, there can be a lot, like especially if you go to the living room or something like that. Okay, so there's always on things, and there's arguments for there as to whether or not we should be shutting off our Wi-Fi routers at night, all that kind of stuff. But there is. So Berkeley did a study, and these statistics are actually going on about a decade old. There have been some changes, and I'll update you to some of these changes. But I've got a list here, tables and tables of data, okay, considering what's called standby power, right? Power when it's on versus power when it's off. So does anybody want to take a guess as to what a desktop computer uses, okay, while it's on? In watts. Average desktop, not some big video card or anything in there. It's about 75 watts on average. Okay, so those of us with bigger gaming rigs, right, 300 to 400 watts, okay, while we're playing a game. Okay, yeah.
The 6 RGB fans.
When the computers are in sleep mode, any idea how many watts they're drawing while asleep?
75.
On average, it's 21 watts. Across a lot of different devices, they just averaged it, right? The sleep was, 21 watts on average. When turned off, start, shut down, power down, the average power consumption was 2 watts. Okay, wait, that's not bad. Wait. Okay? It's off. Why is it drawing any power? For what? I mean,
They gotta listen to me.
when it's asleep, when you have it in sleep mode, I kind of understand, right? You got to wiggle the mouse, hit the keyboard, do something to get it to wake up, or maybe even it needs to wake up to do an update and then go back to sleep again. Right? There's a sort of a purpose to a sleep mode, right? But turned off, why is it drawing power? So that's on average 2 watts per desktop computer. There's at least one desktop computer in just about every home in America. And if they're turned off, which they hardly ever are, right? That's a lot of electrical power, right? That's just wasted. It's a vampire, right? Sucking us dry.
Is it because it's using that energy to wake up faster when you boot it back up?
It's simply drawing electrical energy because the power supplies aren't very good. Laptops, on average, run about 30 watts. If they're charged, 45 watts if they're charging. The power supplies, the bricks, these things, simply plugged in, not doing a thing, 5 watts. Okay? Charging, 85 watts. If you got an 85 watt charger, 75 watts, right? Okay. But the point is that just plugged in, not even hooked up to the computer, 5 watts on average, right? Big energy vampire right there. Televisions don't fare much better. Okay. This list has fax machines on it. All right, so let's talk about set-top boxes, digital cable boxes, and DVRs. Okay, so we'll just do DVRs because everybody has a DVR, right? On average, turned on while watching TV, 30 watts. Not bad, right? It's okay. Turned off, 30 watts.
Wait a minute. Hold on a second. You gotta record your mom.
That's right. Okay, the DVR has to be ready to record when you tell it to record. Okay? And so until 2018, cable providers didn't have the device turn off. You had a button, right, that turned it on and off, but all that did was put the screensaver on or something, right, on your television. It didn't do anything else. It kept the box was on 24/7 at 30 watts. Okay? In 2018, the federal government required energy efficiency standards for set-top boxes. They are now required to go into a standby state when they are not being actively used. Okay? So they'll power on to record your show and then power sleep. Okay? But it only drops down to I think the federal standard is 5 watts. It has to be below 5 watts in its standby mode. Okay? 2018 was a big year for energy standards, and our current administration is trying their best to get all those repealed. So televisions are bad. Does anybody want to know what their CD player is doing?
Want to take a poll who has it? That's not the right spot.
Your microwave oven with the door closed, not cooking anything, is an average of 3 watts. 24/7, right? Game console. On average, while on playing a game, 30. This varies widely depending on the console, okay? But the average is 30 watts. In standby mode, 25 watts.
Oh, no.
And off, 1 watt.
Oh, okay.
No, it's not okay. Because if it's off, it should be off.
It's gonna be a DVR.
Surge protectors. You know those outlet strips with the switch in it that has a little breaker in it, right, to protect from surges? While everything is off, the switch is off, and everything plugged into it has no 1 watt.
Wait, how does that make sense?
When turned on, okay, and all the devices, the surge protector itself, 0.8 watts.
What? Wait.
It consumes more power when it's off.
What?
So, what you'll find in my house, okay, is I have the outlet strips that are not surge protectors. They're just switches, okay? Because that switch is a hard kill, okay? And to that, I have attached the television, the Nintendo Switch, the DVD, we don't have VCR anymore, DVD player, Blu-ray player, right? Okay, all the different things. And so at night, I can walk over and go, clunk. So I hit that switch, and what do I know? Everything is off. I have no vampires there, right? Now, my router and my Wi-Fi, right? I keep that plugged in 24/7. But my computers, shut them down first. Okay. They have a kill switch, right? Okay. Again, to just keep those vampires from. I mean, why would I pay money for things to just be sitting there not doing anything? Right? It just doesn't make any sense. What?
I was saying that's why you need a nuclear reactor.
Yes, that's exactly what.
Wait,
Okay.
but if they're measuring in like kilowatts per hour.
Not per hour.
Kilowatts hour.
Kilowatt hours.
Those like devices that draw less than 5 watts.
Right.
Just like
But it's 24 hours a day.
Okay.
7 days a week, 365 days a year for one household. Multiply that by the number of houses in your neighborhood, by the number of people in front, and it becomes a national problem.
Is it drawing like there's like less than 5 watts per hour, or how is it like
5 watts. It's just 5 watts. So if it's on for an hour, then that's 0.005 kilowatt hours
Yeah, so it's like
Yes, but
thousand of the same.
times 24
yeah.
Oh, okay.
times 365 times
How-
how many of these devices times 10 or 15 of these devices in your house, right? Yeah, on an individual level, it's not so bad, Mr. Bailout. But in terms of energy efficiency, what is PG&E doing this summer? Shutting off electricity. Why? Because of climate change. Let's just straight to the heart of the issue, right? They're shutting off power because of climate change. It's called wildfires, okay? But it's climate change nonetheless, okay? They have to shut that down because they had big fires last summer, right? The amount of energy the PG&E needs to produce depends on something called the load. And the load fluctuates versus time of day and when we're using devices, right? At night, the loads are much higher than they used to be, right? We just have devices that are on all the time. And it takes energy, changes the climate, does all kinds of stuff.
Why do DC power, like AC to DC power supplies all have standby, or dead, like off power? So like laptop chargers, cell phone chargers.
That's something we can talk about after we get to AC. Okay? It's in the conversion between them that you run into trouble. Yeah. Okay. It's not just an inverter. It has to do with cleaning up the signal, and the signal processes are constantly running, even if current's not being pulled. So anyway, it's a problem. It's a big problem, and the former administrations in this country did a lot of work. You remember LED light bulbs? Right? They got rid of incandescent light bulbs. What's the Trump administration done just last month? Didn't hear about this?
No.
They brought back incandescent light bulbs. They repealed all of the regulations banning incandescent light bulbs. What's the problem with an incandescent light bulb? If it says 100 watts, how much energy does it take? 100 watts. An LED light bulb can produce exactly the same illumination at 6 watts. Exactly the same brightness. 6 watts versus 100 watts. That's a 94% reduction in the amount of electricity that is being used. Right? And the Trump administration just said, you know what, LEDs are stupid, let's bring back the incandescents. Right? So, this doesn't make sense. It just, I mean, unless you look at it from the point of view of people make money by making incandescent light bulbs, right? So, yeah, beware lobbyists. They're terrible.
The only valid argument I've seen for incandescent is like the light quality is better. So like an incandescent.
There is an argument to be made that if you are doing professional photography, an incandescent does give off more wavelengths than, say, an LED bulb does, okay? But human beings cannot tell the difference. Our devices can. Our cameras can tell. But cameras do this thing called automatic white balance to fix that, okay? But no, there's no argument for, I need to have a certain kind of light. There are people with things like seasonal affective disorder that need a broad spectrum lamp, but you can do that in LEDs. You don't need a filament to pull it off. Anyway, we can get really sidetracked on energy policy. And we won't, because we need to talk about batteries. Okay? And you're going to be very disappointed because I am not going to go into the chemistry of batteries.
No.
That requires chemists. Are there any chemists in the hall? Didn't think so. So, we will, just to sum up, okay? Why don't we have electric cars? Why don't we store energy in batteries in the electrical grid? It's because the batteries suck. The batteries we have right now suck. They are terrible, okay, at just about every metric. Okay? Energy density, storage of energy, energy losses, all of that kind of stuff. We do need better battery technology. Okay? The car with the longest mileage for electric car battery, I believe, is the Tesla Model X. I think at its highest price point, which is something like $140,000, you can get a 500-mile battery in that thing. Okay? A tank of gas, a 22-gallon tank of gas at about 30 miles per gallon can get you like 650 miles, 700 miles, right? The energy density of gasoline is way better than it is for batteries. Okay? So when it comes to electricity, the problem is always, it's the batteries, stupid. Not that you're stupid. The batteries are stupid. Okay? It really is a problem. So, you want to change the world? Go invent new batteries. And I don't know if you've heard. If you hear every once in a while, they say, oh, some team invented a new kind of battery that charges instantly or discharges, right? Where is that?
They get shelved.
No, it works just fine in the lab. As soon as you try to mass produce it, big problem. Anybody know who the greatest producer of batteries is right now? Tesla. They have the Gigafactory in Nevada, okay, just outside Reno. Panasonic and Tesla got together. They're manufacturing battery cells at the fastest rates. Those are lithium-ion batteries. Those are the kinds you find in our phones and our laptops, all that kind of stuff. There's a problem with lithium-ion batteries. They blow up. Okay. Lead-acid batteries are really heavy, so your mileage goes way down. Okay. Samsung phones famously had a problem. They were blowing up in people's faces. Okay. So there's other battery types, like there's lithium polymers. Lithium polymers are awesome. They charge pretty quickly. They discharge really fast. Okay. I used to use them in radio-controlled cars and planes and stuff like that. The problem is they puncture, they explode. Battery this size, okay, explosion this big, right? It's really violent. Okay. Electric cars have been known, after having been in a crash, a week later they're in the junkyard, they catch on fire. Okay? Because the batteries have been sitting there waiting to just release all of their stored energy.
Wait, but in a car, don't you want a battery that discharges slower than
No, not necessarily. Depends on what you want your 0 to 60 time to be. Right? So, but let's talk about, did you have a question? Go.
The world record for like electric car range was some guy who owns like a electronic waste scrapyard and he like built his own like old batteries and stuff.
Yeah.
Like that.
Yeah, no, you can do it. You can just shove a bunch of batteries on things, but you lose. There's diminishing returns. All right. So, what is it? Physically speaking, we want to talk about the physics. Okay, we know the symbol for a battery. It's got a positive plate and a negative plate, but there is also inside a battery. So, have I told you that the symbol for a resistor is a squiggly line? I don't think I did, but it is. Okay, just good. It's supposed to be nice. It's supposed to be like something like that. Okay, but for me, it's always right because too much time. Anyway, so what I've depicted here is there's a resistor. There's a load. Okay. The battery is attached to it. And by the battery, I don't mean just that symbol. I mean the physical object that is the battery. It consists of two parts. It consists of chemicals and materials that allow for a potential energy difference to be produced. Okay? And that's what the small and big plate represent. But within that chemical structure, there is another kind of resistance called the internal resistance of the battery. I've said it before, I'll say it again. You never charge a battery. The charges come from where?
There.
The conductors, the circuits, okay? They're in the chemicals of the battery, they're in the wires of the circuit. The charges are always just there. So what the battery is doing is it's taking advantage of chemical reactions called redox reactions that exchange energy for oxidation states, and that allows for charges to be given energy. High energy charges come out the positive side of the battery. They then go to some sort of load, right, where that energy is used, and then they come back to the negative side of the battery to be pumped up again by the chemicals. So in a battery, we have two things. We have something called terminal voltage. That's not the voltage that you die at. It's the voltage across the positive and negative ends of the battery. And then there's something called EMF. Okay? It's a really unfortunate name. We continue to use it for historical reasons. But EMF stands for electromotive force. It's not a force at all. Okay? The EMF is a potential. It's a voltage. But it's the voltage that the battery is capable of, but is not necessarily the voltage the battery is producing. The EMF, so the terminal voltage, the difference between the ends of the battery, okay, delta V, is the difference between the EMF, that is a capital curly script E. Again, it's supposed to look, oh, you still have a moment of inertia on board. The symbol for EMF is supposed to look like that or something, okay? But mine ended up looking like that, okay? Minus the current times the internal resistance of the battery. That comes from Ohm's law. Remember Ohm's law? Potential is equal to current times resistance. So I times R is, so I've got voltage equals voltage minus voltage. Delta V, the terminal voltage, what the battery is actually capable of providing in terms of potential to the circuit. EMF, what the battery wants to do, okay? Or what the chemistry of the battery is capable of doing, minus the potential that is basically unavailable or used up because of the internal resistance of the battery. The internal resistance of the battery totally depends on the chemical state in the battery. So as a battery is discharged, okay, what's actually happening is that the internal resistance is going up. It starts at very near zero, very small. So whatever the EMF is, say 1.5 volts, okay, is the terminal voltage. But as the battery goes through those chemical reactions, the internal resistance builds and builds and builds, till eventually the EMF of the battery and its own internal resistance conspire for the terminal voltage to be zero, or so low that the electrical circuit is no longer able to do anything, right? There's just no more energy available for the circuit to do its work. So when a battery is recharged, I die a little inside every time I have to use those terms, okay? When a battery is recharged, in essence, what you're doing is you're providing a way for the chemicals in the battery to reverse their reactions. The internal resistance drops, and you're able to provide the true EMF back into the circuit.
So when you say internal resistance, you're talking about resistance within the circuit or within the battery?
Within the battery itself, within the physical confines of the battery. So we're talking the plates that are in there. So for like a lithium-ion battery, it's lithium metal, obviously, and then carbon is another material. And then they use an electrolyte, which is the thing that lets the charges move through it. It's a gel, like a pasty type substance. And those three things together conspire with the magic of chemistry that I'm not going to explain to you at all, right? To provide these potential differences. As the reaction proceeds, the reaction provides energy to pump charges through the circuit, right? But as you do those reactions, you run out of reactant. A rechargeable battery allows you to reverse the potential direction, reverse the current, which reverses the redox reaction. What's the opposite of a redox reaction? Oxidation, right? Okay. There's a reduction oxidation, and then there's, I'm not a chemist. I need a chemist, right? But then you reverse it, and that changes the chemical state back to its original state where it had low resistance. So a physicist will always talk about internal resistance, because that's what matters to us. a chemist will go all off on, well, electrons, right? Okay.
So is IR internal resistance or amperage times?
It's current. It's the current that is in the circuit times the internal resistance of the battery.
So R is the internal resistance.
Little r is the internal resistance. All right. Let me show you a video to try to underscore what it is I'm talking about here. Okay? Because when you measure the potential, the voltage of a battery, it can lie to you, right? There's a difference between what the battery's voltage is and what its voltage is under load.
These two sets of batteries appear identical and show approximately the same reading on a voltmeter, but there is a difference. When a light bulb is connected to this set of batteries, the bulb lights and the voltage of the batteries remains about the same. When we do the same with this set, the bulb fails to light and the voltage of the batteries drops to nearly nothing. This set of batteries has been heavily used and has a high internal resistance.
Right? When it wasn't connected to the circuit, it was showing potential, wasn't it? Okay? So back here, when there's no current, when there's no charge moving through the circuit, then your terminal voltage and your EMF, right, are the same thing. But the internal resistance of those heavily used batteries was so high that when you switched it and current tried to flow, right, it took away from that EMF. There was nothing left over for the external parts of the circuit. So a discharged battery still has potential. It's just that potential can't get out, right? It's all tied up inside of the battery. Whereas a fully charged battery, one that's ready to go, has a low internal resistance. Now, that's kind of a long talk for something that we're not ever really going to use. For us, we're always going to assume that the internal resistance of our batteries is 0. We're going to use perfect batteries in all of our circuits, in all of our calculations. But I wanted you to appreciate and understand what's going on to a battery, right? Because it is confusing. We use those terms incorrectly, don't we? Charge a battery, discharge a battery. None of that's happening. What is a battery? What's its role in a circuit?
To provide potential.
Provide potential. That's it. Potential energy. Okay, give charges energy so that other parts of the circuit can then use that energy to do something. Create heat, create light, play video games, whatever it is, right, that you're trying to do in the circuit. All right. And really, our future as a species depends on our ability to get good batteries. In order to fix so many of our problems in terms of energy, energy storage, climate change, all of that sort of stuff, we need to find a way to electrify, right? And get off of the fossil fuels. And the way to do that is to store stuff in batteries. Just one anecdotal story. I'm a bit of a fan of Tesla and SpaceX, not so much Elon Musk. But I do like what SpaceX is doing. I cry and get giddy every time SpaceX does anything. But I don't know how many of you know anything about Australia. Okay, nobody does because, well, it's Australia. But Australia, one of the southern states of Australia, near the city of Adelaide, was having Southwest Territory, was having power problems. Their power, they're using fossil fuels, and the oil plants were old and they were breaking down, and the infrastructure was bad. And they were going to have to spend something like, I can't remember what it was, $500 million to upgrade everything and do all this kind of stuff. And they just didn't have the money for it. Elon Musk tweeted the Australian government and said, give me, 90 days? And I will fix all of your grid problems for $100 million. Or it's free. Right? He said, I'll come down, I'll install solar panels and batteries. Okay? And this had never been done before by Tesla. Tesla, the old Solar City, got bought out by Tesla. Right? And so he said, Australian government, I'll sign the contract today. Calendar day starts tomorrow. If I can't deliver a solution in 90 days to all of your power problems, it's free. Otherwise, if I do it in less than 90 days, you owe me $100 million. The Australian government went, sure. Like, what can we lose, right? Okay. It was a big marketing stunt by Elon Musk, right? Okay. In 45 days, they had the project done. Okay. Since then, the amount of fossil fuels that the Southwest Territory has used plummeted for something like 95% of their power by fossil fuels to like less than 3%. The system is working so well. It's solar power, right? And they generate excess during the day and they shove it into Tesla batteries during the day, which then run at night to provide, power at night when the sun isn't out, right? But it works so well that they've actually dismantled all but one of their fossil fuel plants. That fossil fuel plant just sits there as a backup, right? No, he did. Made a lot of it. It's a very disruptive technology. He then pulled it off again on, I think it was Vanuatu, which is an island in the Pacific. That entire island country now is run by Tesla, like solar power by Tesla. Hawaii is doing it. Lots of places. Who's the number one installer of solar panels now?
Tesla.
China. China by a long shot. Like, you think Germany and France? No. Okay? China is like blitzing the place.
If you want a really cheap solar installation, get Chinese panels but American controllers.
Yes. I have American panels and American controllers. But that's because back then Chinese panels didn't exist. My solar system on my house is 10 years old. Right? So.
Inefficient.
Oh yeah, it paid for itself in 6 years. My system was $28,000, and we took out a loan on the house to pay for it. In 6 years, I had paid that off. So for the last 4 years, I've been making money. And over the time that I will have the panels, 30-year lifetime, I will make something, back when I calculated it before they changed the energy rates in California, I was going to be in the black by $75,000.
$75,000.
$75,000 over 30 years. Okay? My electrical bills went from $500 to $600 a month in the hot months, September, October, to $500 to $600 a year. Total, the entire year. It is insane. It's a really good way to save money. And I get to hug trees and kiss the planet and save the whales. Right? Which is also important to me. But, I had a family of 4. This does not work for like 2 people. Okay? It doesn't make financial sense for 2 people. Right? But for a community, right? What is California requiring all new houses since 2017? They have to have solar. They have to have solar on them. Period. The end of argument, right? Okay? Because you can offset so much. Anyway, we got let's talk about this. I could do energy policy literally for the rest of the semester. All right. So, we know about series and parallel connections. What would resistors in series look like? They would look like resistors. Good job. Okay? All right? I'll include batteries on these diagrams because batteries are important. So 3 different resistors, all with different resistance, all that sort of stuff, right? All hooked together in series, one after the other, right? Boom, boom, boom. Think about the current. Think about a charge. A charge has to go through one to get to another, to get right to another. That's what series would be. And what would parallel look like? They would look like they're hooked up in parallel. And what is parallel? I mean, what's the dead giveaway for parallel? The junctions, right? Okay. But even more important than the junction is the fact that in a parallel circuit, all the top sides of the resistors are at the same potential. See how the big plate of the battery is connected to the top sides of all 3 of those resistors? And the small plate of the battery is connected to the bottom side of the resistors. So I keep saying top and bottom. When I say top and bottom, what's the picture I've got in my head for a circuit?
Sideways.
Remember how the battery pumped it up? And then the resistors were like waterfalls coming down, right? So when I look at this, I see the big plate of the battery, that's where it's pumped up, right? So all three of those waterfalls start at the same height. And they all end, the bottom of the waterfalls are all at the same height. But maybe the shape of the waterfall is different, okay? They all have different resistances, but the potential drops across those resistors all equal. Over here, right, one waterfall has to lead into another.
The board that we used yesterday during the lab, it did have resistors underneath, right?
Yes, it did.
Were they connected in series?
No, they weren't connected at all. Okay?
Oh, I guess.
The boards used an old kind of voltmeter called a galvanometer to show the different voltages as you move the probe around. With our modern digital multimeters, we no longer needed those resistances to provide the measurement. So yeah, those. I mean, we could just take them all off that board. They don't need to be there anymore. All right. So, but let's take a look at like what's going on with current and voltage. The rule is Ohm's law. If we're talking about resistors in circuit, then we're talking about Ohm's law because it's about potentials, it's about currents, it's about resistance. So let's take a look at the current and voltage in series versus the current and voltage in parallel. In series, what can you tell me about the current in all three of those resistors?
It is the same.
It's equal. It has to be the same. Whatever amount of charge goes through R1 per second has to go through R2, has to go through R3. There can't be any differences there. So that means that my currents, or a statement for current, would look like that, right? Over here in the parallel case, are the currents the same? No. Matter of fact, if 10 charges per second come out of the battery, how many charges go through R3 versus R2 versus R1? Depends. Depends on their resistances, doesn't it? But the total sum of currents through all three of those has to equal what? What came out of the battery, right? So they might divide up, like the top one might be 5, and the middle one might be 2, and the next one might be 3, but they have to add up to the total, right? So the current here is, I like to call shared, or is the sum, right, of all the currents through the individual elements. But what can you tell me about the voltage in parallel? It's the same. I already told you that. I gave you that argument, didn't I? Okay. So here, the voltage is equal, right? Dot, 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 if we had more. But what's going on with the voltage in, or the potential in series? It adds up. So if you've got 10 volts coming out of that battery, then the first one takes 5. What's left for the other two? 5, right? So if one takes 1 volt, the other one has to take 4 volts, so on and so forth, right? You're adding those all together. So the total voltage is going to be the sum of those voltages. All right. In terms of voltage, then, okay, for the entire circuit, okay, if we write down Ohm's law, okay, for these elements, did I do this? No, where is it? So the fact that the currents are all, the voltages are all added together here. Page back. There it is. I can write down this voltage as the current in the circuit times the total or equivalent resistance in the circuit. And then I can write each one of these individual voltages. I1 R1 plus I2 R2 plus I3 R3. Right? Just writing down that voltage statement in terms of Ohm's law. But what do I know about the total current in the circuit and I1, I2, I3? They're all the same. So what can I do? I can go ahead and just drop those all out, can I? In which case, the total resistance of a combination of series resistors is found by doing what? Adding them all up. So there's your series rule. Important to note that the current is identical and the voltage is shared. And the total sum of resistance is the sum of the resistors. If we go over here to the, if we come over here to the parallel case, right? Then if I write down this current, that current is the total voltage divided by the total resistance or equivalent resistance of the combination. I1 would be V1 over R1, V2 over R2 plus V3 over R3. And what do we know about the voltages in parallel? They're all identical. So that means the inverse of the equivalent resistance is equal to the sum of the inverses of the individual resistors in the circuit. So if we're adding resistors in parallel, what do? Add their inverses and invert our answer. We remember that the current is shared, but the voltage is the same. Again, those are the important rules for parallel. For series, we just add up the resistances. The current is the same, and the voltage is shared. Does anybody see a potential problem? Ooh, pun intended.
Which one?
No? This is exactly opposite the rules for capacitors. Right? When capacitors hooked up in series, what do? Add their inverses. And if they're hooked up in parallel, what do? You add them up. It's exactly opposite, and to this day, I have to check my notes every single time. Okay? Because I can't remember which way is which, and forwards and backwards. Okay? So just be careful there, right? Don't fall trap to thinking that parallel is always adding inverses. It's not. Right? Depends on whether we're talking capacitors or talking resistors. I saw some hands out there. Carlo, somebody else.
Is there a difference between the small r and the big r?
The little r I wrote for the battery, that was internal resistance. Yeah. Big R typically for resistors in a circuit. Yes? Okay. So now that we have the rules, let's see why series and parallel do their thing. And then we'll get into the thick of it.
The resistance of an electric resistor is proportional to its length, inversely proportional to its area, and proportional to its resistivity, or its tendency to inhibit the flow of electrons. This tendency to resist is something all materials have, but to varying degrees. Adding resistors to a circuit, one after another, has the same effect as making one resistor longer. These are called resistors in series. Putting resistors side by side increases the area through which the current can flow. These are called resistors in parallel, and they have a lower resistance than either one alone.
So we saw mathematically, right, that we're adding the inverses, which drops the total resistance, right? They're arguing from the idea of cross-sectional area. Both are true, right? Both are, one's math, one's concept. What's that?
What increases resistance?
Adding them in series, because it's like adding length.
So
In the video, she said that like if you have a series, you just like basically the same thing, just add it together, right?
Yeah.
So what if they're in different materials?
Doesn't matter.
That doesn't matter.
The overall resistance, right? You just have a different row. You just
Oh,
keep adding it together.
Or at different locations.
That's a different circuit then, isn't it? All right, this video is going to pose a question. It involves light bulbs. Incandescence. Old video.
Here are 3 light bulbs. We'll hook the first bulb up to house current, then hook the other 2 bulbs in parallel to the first, one at a time.
You excited yet?
Oh, she's using the one.
The brightness of the bulb
No one
stays
in.
constant as each is hooked in.
Used to.
Used to have 2 hands. Now only have 2.
Now we'll again hook up the first bulb, then hook the other 2 bulbs in series with it, one by one. How will the brightness of the bulbs change?
Okay, so you've been shown that when they're wired in parallel, the brightness stays the same. Turn to your neighbor and discuss what's going to happen to these and why, if they're hooked in series. All right, do you have it? That means it's brighter. No change. Dimmer. Why? Resistance going up. Okay. And before, the resistance was going down, wasn't it? Okay. But also, in parallel, the brightness stayed the same. That means that each one of the... What's the rule for voltage in parallel? It's exactly the same. So each of those bulbs had exactly the same potential. When we go up in series, what happens to the voltage? It gets shared. So according to the experiment, the voltage determines the brightness of the bulb. Right? So now if we're going to have to share that potential, share that voltage, the brightness should go down. Resistance is going up, if you want to think of it that way.
The bulbs dim as each new bulb is added.
And notice, they have to all go off to be able to reconnect and bring it back. And this tells me absolutely nothing. Nothing good. And it went by too fast anyway. Okay. All right. Let's do...
Why wouldn't you just have one long resistor instead of having two separate side resistors?
Okay, so this is a good question. Everybody hear Carlos' question? Why not just have one resistor and not have 5?
Because if it breaks, then
Let me show you why. Here is an electrical circuit. It consists of a potential source. Could be a battery, might not be. But whatever it is, it's providing 15 volts. It is connected to not 1, not 2, not 3, not 4, but 5 resistors. Okay? I will label them as resistor 1, resistor 2, resistor 3, resistor 4, and resistor 5. And for the sake of just the example and simplicity and helping you keep track of the process, the name of the resistor is also its resistance. In other words, R1 is 1 ohm.
Oh.
R2 is 2 ohms. R3 is 3 ohms, 4 ohms, and 5. You get it? Okay? So I'm only doing that to help you focus on the process that's about to happen and not get befuddled with the numbers, right? Usually these resistances are measured in like hundreds to thousands to tens of thousands of ohms, depending on what you've got going on here. So Carlo asked the question, he said, well, why not just have one resistor? Why have 5 resistors hooked up like this? Why not just have one? The answer is, these resistors could represent light bulbs in a circuit somewhere. They could represent different appliances in your house. A resistor doesn't have to be the actual thing. It can be anything that's using electric potential energy in a circuit. Okay? So, whether these are appliances in your house, light bulbs, whatever, right? You could have a necessity. The physical arrangement of things might necessitate all of these junctions and these arrangements, right? But as far as that power supply is concerned, it doesn't see the individual things. All it knows is that there is a total resistance that it's connected to. Therefore, it's going to provide a certain amount of current based on that total resistance. Our job here, the problem-solving method, or the problem that we have before us that we need to figure out, is what is the current and voltage through every single element of this circuit. Ultimately, we actually want to know the power dissipated by this circuit, right? But to know the power, we need to know what the powers of all the individual things are, right? So we want to find the power of every individual element. We want to find the total power of the circuit. We want to know everything there is to know, right? And so the way that we're going to do that is by using the rules of series and parallel reduction, right? Bring this down to the simplest possible circuit that can exist. What does the simplest possible circuit always look like? A battery connected to something, right? In this case, a single resistor. So we want to collapse this thing down and then uncollapse it. This is a bit like electrical origami, right? We're going to do a bunch of folding, right, to get something, and then we're going to unfold it. And when we're done, we're going to be able to see where all the folds happened and what all the different things that needed to be, right, in order to get to the thing that we want. So that's what we're doing. My advice, when you're doing the math is not going to be hard. Okay? Unless you have trouble like me with division. Okay? You're going to be good. Okay? The problem, the difficulty here, okay, is conceptual. The rules of series and parallel and what's going on with the voltages and currents. And the accounting. These, to me, are accounting problems. An accountant does what? Keeps track of numbers. That's all an accountant does. And they get paid lots of money for it. Okay? Because apparently you can invent money by accounting the numbers in different ways. So, accountants keep track of numbers. And that's what you have to get good at if you're going to survive circuits. Those of you who are going to be electrical engineers, this is your life. It gets more complicated. But essentially, you are going to be really good accountants. Okay? And you're not going to pull the same tricks that violate physical law that financial accountants do. Because you have to obey all the physical laws. So, first step. Make a table. Organize your information, right? Get this down. My table, I'm going to have R, I'm going to have V, I'm going to have current, and I'm going to have power. I kind of like to do RIP-V, R-I-P-V, but to make a little spreadsheet. Let's see, how many things have I got in my spreadsheet? I've got resistance 1 ohm, 2 ohm, 3 ohm, 4 ohm, and 5 ohm, right? So this is resistance in ohms, voltage in volts, current in amps, and power in watts. All right? Make some room. As I discover something in my problem-solving method about one of these physical elements, I'll write it down in the table, right? Just to keep things organized. All right, what's the first thing that I can do to make this circuit simpler? 2 and 3. Why are you looking at 2 and 3? Because you can look at those and tell that they're in parallel with each other, right? Again, personally, I find it easiest to look as far away from the battery as possible. Okay? Go as far away from that. Like look at the junctions. I just try to find 2 junctions where wires are breaking apart and coming back together again, right? And I start there, and then I work my way towards the battery. Ms. P could probably tell us some much better ways to do this, okay? But at this basic level, that's a safe way to do it, okay? So I'm going to combine those 2 together, okay? What will my circuit look like once I combine those 2 together? Well, I'll have battery, R1, there's R5. So here's 5, here's 1. And then I'll have some combined resistor there, and I'll have R4 down here. Okay. Let's find out what that combined resistor is. They are in parallel, so what do I have to do? I have to add the inverses, don't I? 1 over 2 plus 1 over 3. Okay. And then I've got to invert that answer, right? So my equivalent resistance turns out to be 1.2 ohms. So I'm going to call this one R1.2. They were in parallel with each other, so I add their inverses, right? Okay, what's the next simplification I can make? The 1.2 and the 4, how are they connected? They're not in parallel? But they're right next to each other. There's no junction between them, right? There's a direct path from R1.2 to R4 with no junction in that path. So that they are in series. And a series combination of these 2. How do we add resistors in series? We just add them, right? So the equivalent here is 5.2. So what does my circuit look like now? The battery, R1, R5, and R5.2. Now, why didn't I just put all 3 of those in series with each other? I have to obey the junctions, right? Okay, I've combined 1.2 and 4 together, but that combination of 5.2 is in what? Series or parallel with R5? It's in parallel. There's a junction, right, between those resistors. And so now I have to, I'm running out of colors. Now I have to combine those 2 together. And how do I combine those 2 together? I have to invert their values and then invert my answer, which I did, I believe correctly, 2.55 ohms. So now what have I got? I've got battery R1 connected to R2.55. And what do those add up to be? That adds up, because they are in series, to 3.55 ohms. So what we've discovered, okay, we've gotten down to the simplest possible circuit, right? Okay, I didn't draw really the last step. This is what it would look like, right? It would be a battery connected to a single resistor of 3.55 ohms, right? Okay, 15 volts connected to 3.55 ohms. So as far as the battery is concerned, it thinks that the total resistance in the circuit is 3.55. what can we now determine about the circuit? Total current. How'd you figure that out? You meditated on it. Ohm's law. We know the total voltage in the circuit. We can find the total current if we know the total or equivalent resistance. Okay? So, let's find out what that current is. It's the only thing we don't know, right? That's going to be 15 volts divided by 3.55 ohms, which gives me 4.23 amps. Can I fill out my table yet? Not really, right? That 4.23 amps is for the entire circuit. Okay? So there's nothing I can really fill out about my table. But what I need to do now that I've folded my origami all up, okay, and got it down to a small piece of structure, now I've got to unfold it. I've got to work backwards, undoing what we did, and at every step, figuring out what's physical and real in the circuit. And by unfolding, I mean we take a step back, don't we? And we realize that this 3.55 ohm resistor came from a true physical resistor in my circuit, the 1 ohm one, and then this 2.55 ohm one. Those were hooked up in series with each other. And what do we know about resistors in series? Their voltage is shared, but their current is the same. So if we know the current is 4.23 amps through the 3.55 ohm resistor, what does that mean the current has to be through the 1 ohm resistor? 4.23 amps. And what does the current have to be through the 2.55? 4.23 amps. So I'm going to come over here to my table, and I'm going to write down that I now know the current. 4.23 amps, right? I've discovered that's an actual physical resistor. I'm going to record that information. So there is 4.23 amps in a 2.55 ohm resistor. If we know the resistance and we know the current, what can we figure out? The voltage. The voltage in my 2.55 ohm resistor will be the current, 4.23 amps, times the resistance, 2.55, which is going to be 10.77, because I can read my own writing. 10.77 volts. All right. We've now discovered something about the 2.55 ohm resistor. Unfolding that one more step. Where did the 2.55 ohm resistor come from? Came from a parallel combination of R5 and the 5.2. Which of those is a real resistor in my circuit? R5. So, we know the voltage is 10.77 volts. Right? It's the voltage there and it's the voltage there. And how do I know that voltage is the same in both of those? They're in parallel. And the rule for parallel is that voltage is identical. Can I write down anything in my table? Yeah. R5 has got a voltage of 10.77 volts. All right. Now that I know the voltage in the 5.2 ohm resistor, what can I discover? Apply Ohm's law. The current in the 5.2 will be the voltage divided by the resistance, right? I'm using Ohm's, no, come back. I'm using V equals IR everywhere, right? So I told you I'd be beating you over the head with Ohm's law. Voltage 10.77, resistance 5.2, 2.07 amps. So where did the 5.2 ohm resistor come from? R4 and the R1.2, which are hooked up how? In series. What's true about series? Current has to be the same. So that means this one has 2.07 amps and this one has 2.07 amps. Have I discovered anything about one of my physical resistors? It's R4. So R4 is going to have 2.07 amps. Now that I know the current and resistance of 1.2, what can I discover? The voltage. 2.07 times 1.2, 2.48 volts. Where did the 1.2 ohm resistor come from? The parallel combination of R2 and R3. So what do I know about R2 and R3 now? I know what their voltage is. 2.48 and 2.48. Because in parallel, voltage is the same. All right. Before we do anything else, let's talk problem-solving method. First step when you're confronted with a circuit is to do what?
Make a table.
Simplify it. Make a table, simplify. Bring it down step by step. Redraw the circuit if you have to. You probably do. Okay? You're going to want to do that. Now that you've got it down to its most simple setup, what do you find? The total current. Now that you have the total current, what do? Go backwards. Look at every step you took to combine things in the circuit and figure out the thing that you are missing. If the resistors are hooked up in series, the currents will be identical, which means you can find the voltages. If they're hooked up in parallel, what's identical? The voltage, which means you can find the currents. It's a little puzzle, isn't it? Okay? And you keep working your way back until you figure out everything that's a true physical element in your circuit. Now, the last thing we got to do really is complete the table, right? Okay? Since we know current and resistance for number 1, can we find the voltage? Yes, sir. V equals IR, right? For number 2, I know voltage and resistance. Can I find current? Ohm's law. Ohm's law. Ohm's law. Right? You should be really calm by the time you're done with the circuit. Meditated on it a while. Over and over and over again. Just chant it to yourself. Om. Because believe me, you're going to need it. This is just above thermodynamics in my book of, oh, please make it stop. I don't like circuits at all. The reason I don't like circuits is because they don't like me. We had a joke. I was the butt of the joke. At BYU, Brigham Young University, religious institution, right? So we have an honor code on campus, no alcohol, no drugs, no smoking, none of that stuff, right? On campus. Or supposedly off campus. But while you're on campus, no smoking, no drinking, no coffee.
No coffee.
Church of Jesus Christ of Latter-day Saints, we don't drink coffee, we don't drink alcohol. So the joke was, right? Dave Balo in circuits class, and this is why it was funny. In circuits, you build circuits, and it's really frustrating because you build circuits on these boards, and if there's little tiny disconnects and things, you get shorts. It just never works, ever. My lab partner, she was brilliant. She always got it to work first time. I sat there screaming out loud half the time, but usually internally, right? Frustrated that things weren't. Anyway, we had these devices that were called potentiometers. Okay? They are a variable resistor. You turn the dial. If you've ever turned the dial on anything, you're adjusting a variable resistor. It's potentiometers. Okay? And it has 3 connections on it. And for the life of me, I could never sort out which of the 3 I needed to use. Okay? They taught me over and over again and never worked. When you hook up something wrong in an electrical circuit, it breaks. And the way it breaks is it usually lets out the magic blue smoke that is required to make an electrical circuit work. The reason the electrical circuit stops working is because you let the magic blue smoke out. Okay? Usually in the form of burning out a resistor or burning out one of these potentiometers. I was notorious for burning out potentiometers. The teacher started to threaten me, you're going to have to start buying them for the school. Because every single time you grab one, you burn it out. And when you burn out a potentiometer, it goes poof, like it just erupts into this cloud of smoke. Okay? Right? The short version of the word potentiometer is pot. And so the joke always went, oh, there's Belo smoking pot in circuits class. Right? I smoked a lot of pot in my circuits class. Believe me, it's the closest I've ever come to wanting the actual thing. I hated that class. Oh, I hated that class. Never gotten along with circuits. Ever. It's just chasing shorts everywhere. It's like, oh my gosh, what else can go wrong in this circuit, right? I've got 100 junctions and every single one of them doesn't like me.
So, back to this question, why would you not want just one really long one and then just like a bunch of them?
Because R2 and R3 might be your coffee maker and your microwave in your kitchen.
Okay.
Right? Okay? There are actual physical reasons for way circuits need to be laid out. Right? Those could be 2 light bulbs over in some part of the circuit that tells people that their device is on standby, right? Versus when something else is going on in the circuit, right? There's actual physical reasons behind why you would lay something out. This particular circuit is just one I made up for illustration purposes to do a bunch of series in parallel over and over again, right? But there are other reasons, like in your house, you've got a bunch of circuits of things wired in parallel, and then those are wired in series to circuit breakers. You don't ever want to wire your circuit breaker in parallel. It's no good. We'll talk about why later. But, I mean, there's physical reasons why circuits have to be the way they are to do different functions. As far as the potential sources are concerned, they don't care about the physicality. They just care about what the totals are. And we can find out everything else. Let's go find out everything else. Voltage for number 1 is 4.2, because I can multiply by 1. This is 1.24 and 0.83. This one becomes 8.28. And this one becomes 2.15. Now that I've got all of those voltages and currents, how do I find the powers? It's current times voltage. Or you can do I squared R. You can do V squared over R. I don't care which one you use. I'm going to use current times voltage. And usually at this point I've got this in Excel anyway, and so I just program it to just calculate it all for me. 17.9, 3.08, 2.06, 17.1, and 23. All right, are the different powers that are there. All right, how do we check that we did any of this correctly? You don't. You just go smoke pot. Add up all the voltages? Can I just add all those voltages? What should happen? If I add these all up, I should get, because you got to conserve energy, right? Energy equals energy. If I add all those up, does it add up to 15? No. You can't do that. Why not? Because there's parallels. What about the currents? The current should add up, right? I can't have more than 4.23. So don't add the voltages and then feel, I've failed. No, okay? Now notice the 2.48 volts you can only use once. Because that's a parallel. But that's going to drive you nuts, right? You might as well just do the problem all over again. Look at the power, though. That power does add up to something, doesn't it? And what should that power add up to? the total voltage times the total current. 4.23 amps times 15 gets me 63.45 watts. And if you add up all of those numbers I gave you right there, you get 63.5. So a little bit of round off error, right? But the power should always work. If you've done it right, you can take the total current and the total voltage to find the power dissipated in the circuit, and the sum of the individual powers of all those elements needs to be the same. If it's not, something has gone wrong. That is conservation of energy, right? And that is the statement that will always work, regardless. Those of you who want to be electrical engineering majors, I am open to counseling you on your future career choices. I will see you maybe this Friday in Grass. You have, is it 2 homework assignments due this coming Monday? 24 and 25? This is chapter 26, I think.
I think it's the other way.
27? This 27? Whatever this number is not the homework that's due on Monday. Because we have to do a lot more with this.
Oh, no.